Hello, welcome back to the lecture videos about atomic spectroscopy. And in this video, we are going to talk about atomic emission spectroscopy and several different realizations of that spectroscopy. So atomic emission spectroscopy is based on emitted light. And this is related to the processes that occur in the atom and this everything starts with atoms being on their ground state, which we denote here as M for the metal atom, and with a superscript of a 0, denoting that the atom here is in its ground state. And what is done in atomic emission spectroscopy is that the atoms can absorb energy in the form of heat from the surroundings. So if the atoms are present in a very hot medium, such as, for example, a flame, they can absorb this heat and go to higher energy niveaus, which we call excited states. And we denote these by this middle M and with a superscript of star. So this denotes that the atoms are at their excited electronic states. And once at their excited states, the atoms can relax back to the ground state. But this can occur either through an emission of a photon, which we can use in atomic emission, or also through emission-less transition. So this is by, again, giving up heat. But what we are interested in atomic emission spectroscopy is the process where the metal atoms return to the ground state from the excited state with the emission of a quant, so emission of light quant. And of course, for one metal, there is not only one excited state, but on the example of sodium, we can see that there are multiple different excited states that differ in their energy. And this also means that if the excited state is relaxed back to the ground state, then these different states release photons with different wavelengths, so they have different energy. And on the example of sodium here, we can see that some of the most energetic quanti that can be released are with the wavelength of 285, but there are also quanti which are much lower in energy, so longer in wavelength. So for example, 589 nanometers. So for each element, there can be multiple emission lines observed in the spectrum, and also multiple emission lines can be used in the spectroscopy. So how is this occurring in a real flame, for example, that can be used to produce atomic emission spectra? Let's view this again on the example of potassium chloride. So first starts it with the aspiration of the solution and producing the gas phase entities, so essentially particle-like species. And these are then dissociated to form the atoms. And the atoms are first on their ground state. So this is the state that we are not interested in atomic emission spectroscopy. But when these atoms at the ground state can gain energy from the environment, for example, from the flame, then they can turn to the excited state. And from the excited state, they can return back to the ground state with emission of a quanti. So this is what we want to measure in the atomic emission spectroscopy. Of course, we have also competing processes, one of them being the ionization. So if too much energy is given to the atoms, then they also can directly ionize and produce the cations in the flame, and these are not useful for the atomic emission. Therefore, we try to optimize in our processes the ratio of the excited state of the atom and the ground state of the atom, but also at the same time we want to avoid interfering processes such as ionization of the species, or it can also be other interfering processes such as oxidation or formation of some particles that interfere. But the most important is that we gain high concentration of the excited species in our medium where we do our atomic emission analysis. The most influential for optimizing this excited state concentration in the flame or in any other media where we do the atomic emission analysis is the temperature of the atomizer that we are using. And here is an example where on the y-axis we have the excited state to ground state ratio. So the higher the number, the more atoms we have at their excited state. And on the x-axis we have the temperature. So we see how the excited state ratio to a ground state is changing with temperature. And with increasing temperature, the excited state becomes more and more populated. The ratio is exponentially, reversed exponentially related to the temperature. So we see that depending on the energy of the transition, we need to increase the temperature quite a bit to actually have a reasonable amount of excited state present in the flame. So for example, here this value corresponds to the 10 in the power of 10, which means that only one atom out of 10 in the power of 10 is actually in the excited state. So this is a very, very small percentage. And for example, this is for the very high energy transitions. This is true even at 3000 kelvins. So for more energetic transitions, so transitions where quanti with lower wavelengths are emitted, temperature has to be very, very high to produce this reasonable amount of excited state for the atoms. For the lower energy states, where the emitted quanti has longer wavelength, this a reasonable amount of the excited state can be achieved already at slightly lower temperatures. However, we can see that for all independent of the wavelength, the temperature has to be above a few thousand degrees of Kelvin. And generally, we can of course say that the higher the temperature, the more we have the excited state in our media where we do our measurements. So this means that to get better sensitivity, to get more ions in the excited state, we have to increase the temperature of the source where we do our measurements. Of course, this effect is slightly different for different elements. Some elements are very easy to bring to the excited state, and to this group belong elements that are in the left of the periodic table. So alkali metals such as sodium, potassium belong to this group. And here we have also a comparison of the excited to ground state population ratio for different elements. And we can see that at 200 kelvins for sodium line at 589 nanometers, this ratio is already about 0.01%. which is small, but it is an amount that we can account for, which could already give us some kind of sensitivity. While for zinc line 213, this ratio is extremely small. And of course, we see that when we increase from 2000 Kelvin to 3000 Kelvin, then for all elements here, this ratio is increasing. So we have an increasing amount of this excited state present in the flame where we do the measurements. However, this effect is still not sufficient for zinc, for still only 1 in every 10 in the power of 10 atoms is actually in the excited state. And only when we manage to increase the temperature to 10,000 Kelvin, we get a sufficiently high ratio of excited to ground state for the zinc atoms. And of course, also for calcium and sodium, it is increased. But for example, for calcium, the ratio was sufficiently high to do measurements also already at the lower temperatures. But for heavy metals and metals that are to the right in the periodic table, so for which the energy that is required to bring about the excited state, the temperature really needs to be higher to achieve this. So optimizing the temperature for bringing as many atoms to the excited state as possible is very important and is very influential on the detection limits that we can achieve in the atomic emission spectroscopy. So how do we do this emission measurements? This is done with a very simple schematic instrumentation. However, the instrumentation itself can be from very simple to quite complex, depending exactly on what atoms and in which way we want to determine them. The important part is that the sample is introduced to an atomizer, and this atomizer can be different sorts. The most simple ones are flames. And from the atomization, we both atomize the atoms as well as excite them to the excited state. And here occurs also the emission of the light from the excited state when the atom returns from the excited state to the ground state. Thereafter, the monochromator or filter is used to select the wavelength that we want to measure. And lastly, the detector measures the intensity of the light that is passing the monochromator. So the first part that we need to do is to introduce the sample to the system. And most often we analyze samples in the solution form. And in these cases, the first task is to nebulize the sample so that atomization of the element that we want to determine can start. And this is usually done with a nebulizer that is also shown here on the right-hand side. So this is done usually by a coaxial system where the inner capillary here, marked with blue, is carrying the sample, while the outer capillary is carrying the spraying or nebulizer gas. And usually this is oxygen or air, something that is also used in the flame, for example. Or if we don't use flame, then by the same gas as is used in the in the atomizer system. And when this gas, for example, air, is exiting the outer capillary, then it is also nebulizing the sample solution into small droplets through a Bernoulli process. And this is actually used both in atomic emission as well as in atomic absorption spectroscopy. And you will also see it later being used in the mass spectrometry to spray liquids into very fine aerosols. However, in case of solid samples, we have two options. So either we dissolve them and then nebulize them and bring to the atomizer, or if we are using arc or spark as atomization sources instead of flame, then we can also analyze solid samples directly. However, nowadays this is not really very common due to the fact that arc and spark do not allow quantitative analysis. After the sample has been sprayed into a fine aerosol, we can direct this aerosol into the atomizer. And atomization can be brought about either by a flame, which is most common, or by inductively coupled plasma, which has several advantages for metals that are not so easy to excite, such as heavier metals. Or atomization can also be done by electric arc or spark, but they are, as said before, are not so common anymore due to the lack of quantitative information from these atomization sources. Flame is the most commonly used to determine alkali metals, so sodium and potassium. With flame, we mean a propane plus air flame, or it can also be a natural gas plus air flame. Due to the fact that it's propane and it's air usually, the temperature is relatively low. It's below 200 kelvins, and this means that it is also able to bring to the excited state only atoms which are relatively easy to excite. And this means elements to the left in the periodic table, so the 1A group metals, so sodium, potassium, lithium, cesium, for example. And it has been very, very widely used in medicine to analyze sodium and potassium concentrations. And it is still used, but somewhat is being replaced by ion selective electrodes, but it's still relevant method of analysis in these clinical applications. For heavier atoms or atoms to the right in the periodic table, flame is not sufficient to actually cause any significant amount of excited species in the flame. So this means that they almost don't emit, or actually don't emit very much in the flame, and they can't be analyzed. So, for example, as you saw for zinc in the previous example, where at the temperatures for flame, which are about 2000 Kelvin, only a very tiny fraction of zinc was in the excited state. And therefore, to overcome this problem, we need a higher temperature atomization sources. And the most widely used for this is inductively coupled plasma source. In the inductively coupled plasma source, argon is used to both carry the sample to this plasma as well as to generate the plasma. So here, the argon is first ionized by, and this ionization is initiated by a spark from electric spark brought about by a spark from a Tesla coil. As a result, the argon is ionized, producing both argon cations as well as electrons. And now this argon cations and electrons located here are in the field of fluctuating magnetic field. And as a result, the argon cations and electrons start moving, and they try to resist this movement by, of course, by colliding with other particles. And this resistance then causes higher temperature uh, being produced here in the argon plasma. And these temperatures can be up to 8,000 kelvins. And this plasma also is very stable, and so the temperature can be very well controlled. It's not varying a lot, and it is also relatively inert. So meaning that because here no oxidizing species are being added to create this high temperature, like oxygen or air in case of flame, there is no problems of oxidizing our analyte, for example, and therefore this plasma is much more inert. Another important factor is that in this inductively coupled plasma, we have always a high concentration of electrons present here in the plasma, which means that if we have elements that we are wanting to determine and which are likely to ionize, then we can assume that the ionization to excitation to ground state atoms is relatively stable because the concentration of electrons in the plasma is very stable, and this is of a less problem than in case of flame. So lastly, I would also like to mention spark and arc. Electric arc, it has a fairly wide temperature range from 3,000 to 8,000 kelvins. This depends on the electrode materials and also how close these two electrodes are placed to each other. So in case of arc, two electrodes are placed relatively close to each other, about a centimeter to maybe a bit less, and high voltage is applied between these two electrodes. As a result, the electric arc is produced between these two electrodes, and this arc also has very high temperature where atomization can occur. The sample can be here also solid, and it can be placed into one of the electrodes, which may have a small conical hole which is meant to carry a sample. So this electrode, for example, can be a graphite electrode. Or if we are dealing with metal samples directly, then the metal itself can be used as one of the electrodes. So the sample is attached to the place of the electrode. Similarly is electric spark, but here the temperature is extremely varying and can be up to very high, so 4,000 kelvins. However, the problem with both spark and arc is that the temperature extremely depends on the sample, on the length between the two electrodes, as well as other factors. So as a result, the temperature is varying very much, and the arc and spark are not so stable, and quantitative analysis is almost impossible because simply the reproducibility of the temperature is so poor, and as the reproducibility of the temperature is poor, also the excited to ground state of the analyte is very, very unreproducible from experiment to an experiment. And this is therefore not suitable for quantitative analysis. However, for qualitative analysis, it's still possible, and electric spark can be very informative in trying to find very low concentration elements and just detecting them. So now when we have the atoms excited and we are also having them on the excited state, they are returning to the ground state and emitting light. We also need to catch this light and get some kind of signal out of it. And for this, we use a monochromator detector systems. The simplest ones are actually filter photometers, and these are used then for alkali metal determinations in the flame. And in these cases, we actually don't use a monochromator, but we use an interference filter that isolates out the wavelength that we want to measure. So one wavelength for sodium, another for potassium. If we also want to measure calcium, that can sometimes at higher concentrations be also done with flame photometers. Then also this. So we have multiple different filters, and we can switch between these filters to determine the element that we are interested in. However, another possibility is that we register the spectrum, or we register multiple different wavelengths. And there are two solutions for this, either a sequential spectrometer, and in this case, the monochromator is used to scan through the whole spectrum or parts of the spectrum and register the intensity of the light emitted by the atoms in our atomizer. Or another possibility is to register the spectrum all at once, so with a simultaneous spectrometer. And in these cases, we use an array of detectors that are next to each other, and monochromator is used to separate all of the light that comes from the atomizer and direct it to the array of the detectors. This is very similar to the diode array that is used in case of molecular spectroscopy in the atomic absorption. Now, we also have to consider that there are different interferences that may occur in the atomic emission spectroscopy, and these can be divided broadly into either Planck or additive interferences, or to the Analyte or multiplicative interferences. Planck or additive interferences are interferences that are independent of the analyte concentration, and the name suggests Planck interferences, that these can be theoretically taken into account if we would have a perfect Planck. Analyte interferences, however, are interferences which depend on the analyte concentration, and they are divided further into physical and chemical interferences. So one of the types of the Planck interferences are spectral interferences. So these are interferences that come from other species present in the atomizer and that also emit light that are not analyte. So this means that if we would be able to create the perfect Planck that would contain everything present in the sample but the analyte, then we would be able to account for this. Some of the examples incorporate measuring one element where a line of another element is relatively close. This is not very much of a problem if the analyte line is more intensive, much more intensive than the interferent line. But for example, measuring magnesium in the presence of very high concentration of sodium, then the sodium line, which is relatively close to the magnesium line, can become of a problem, because at high concentration, sodium lines become very wide, very intensive, and they may interfere with the magnesium detection. Of course, what can be also here considered as a solution is to just obtain a better resolution of the light. However, in case of instrumentation at hand, we very often cannot scrutinize the resolution, but we have to accept what we have. Another possible interferences here are molecular species. So in the flames especially, molecular bands may occur due to the formation of molecular species that then emit light at a very wide range of wavelengths. So let's see that on the example of a Brin sample. And here we can see in the Brin sample very nice lines. So for example, here for sodium at 330 nanometers, or for calcium at 422.7 nanometers, or for potassium here. But we also see bands. For example, this is now a band for a molecular species, magnesium hydroxide complex. So this is not an atom, it's rather molecular species. And we also see that it's forming a very broad peak here. And of course, if we would be interested in measuring any element in this region, this broad band would interfere with our measurements. Additionally, we also see a continuum spectrum, which is here showed with this increasing baseline with a dashed light blue line, which actually shows us the emitted light that comes from our atomization source. So, for example, flame. And these other sources of light that are emitting in addition to our analyte and that can't be separated also have to be taken into account. And less they are, the better, of course. In addition to these blank interferences, we also may have interferences that are proportional to the analyte concentration or that depend on the analyte concentration. The simple ones is physical interferences, and these are interferences that affect how the atomization process is occurring. So either they affect the sample flow rate to the atomizer, or they interfere with the desolidation process or volatilization. For example, if the sample has very different viscosity than do the calibration standards, then the flow rate of the sample is going to differ from sample to standards, and therefore we will not see actually the same concentration of the atoms in the flame. Also, for example, if our standards are neat water solutions, but our samples contain organic solvents, then these organic solvents burn in the flame, and by this process they also affect the temperature of the flame. And of course, temperature is affecting the atomization efficiency as well as the excited state to ground state ratio. So if we have this fluctuation in the temperature due to the sample content, then we also have differences in the atomization efficiency for the samples. Important are also chemical interferences, and the simplest one are solute volatilization interferences. So these are species that are forming some very, very stable complexes with our analyte, and these complexes are not volatile. So in this sense that atoms of our analytes are not released from these particles. And this results in the formation of solid particles formed from the analyte in the atomization source, instead of forming the gas phase atoms. So before the gas phase atoms can be formed, our analyte is precipitating into solid particles due to the presence of other compounds in the sample. For example, into this kind of interferences class fall different anions that form very stable particles with our analytes. For example, phosphate is known to cause this effect for calcium, for example. To overcome this effect, there is a possibility of adding releasing agents. So these are other metal salts that can be added to the sample, but these then preferentially react with these anions and therefore release our analyte from the interference. Or another possibility is to use protective agents. So these are usually a reagent that form a very stable complex with our analyte, and This very stable complex is then more stable than the analyte interferent complex, but the newly formed complex is also volatile and helps therefore our analyte to become into a gas phase atoms. And a very commonly used protective agent is an EDTA for very many methods. Another type of interferences is the ionization interference, and ionization interference is affecting by changing the amount of our analyte atoms that are ionizing in the source. So we had these three processes: the atoms that can be excited, that can return to the ground state, and we also had the ionization that may occur. So the ionization interferences are changing the ratio of the ionized atoms to the ground state atoms, and therefore also to the excited state atoms. And these are mostly ions that are themselves ionizing very easily, and therefore producing an higher concentration of electrons in our flame. So these are mostly alkali metals that can cause this kind of interference. In order to avoid this, we do something interesting, namely we usually add very much of these very easily ionizing metal atoms to our flame by using an ionization suppressant. So this is a mixture that can contain potassium, sodium, or other easily ionizing elements. And by adding this very much of these easily ionizing atoms, we increase the amount of electrons that are present in the flame to a very high extent, so that if our sample now contains a tiny bit more or tiny bit less of potassium, then this doesn't anymore change the concentration of the electrons very much. So this can then be used to stabilize the ratio of the ionized atoms to the ground state and to the excited state atoms. And of course, we want to often perform quantitative analysis. And for this, linearity is very, very important. And we can have two kinds of interferences that cause deviation from this linearity. At higher concentrations, the problem is usually related to self-absorption. So this means that even at relatively high temperatures, we have majority of the atoms on the ground state. And this means that if our atom was now on the excited state, it returns to the ground state and it emits an quant. Then before this quant can reach out from the flame, there are multiple other atoms that it can meet. And these atoms are very likely to be on the ground state and can therefore absorb this quant. So this means that even though emission occurred, this quanti might not actually be detected because it was absorbed before by a neutral atom. And this is especially problematic in flames because flames have longer optical path lengths compared to, for example, plasma. Another problem is non-linearity at lower concentrations, and this can occur due to the ionization of the analyte. And of course, again, this is less common in case of plasma due to the fact that in plasma we have a relatively high and constant electron concentration due to the ionization of argon in the source. This was shortly about emission analysis of different atoms, and we'll continue with the atomic absorption spectroscopy.